Next we will derive the lens maker formula, and this formula tells the curvature required to make a lens of the desired focal length. Suppose we consider a biconvex lens whose two surfaces have the radius of curvature r1 and r2 respectively, and there is the principal axis on which we take an object O. A ray comes from the object and strike on the first of the interface, and because of the law of refraction it deviates towards the normal. If we consider that outside media is having refractive index mu1 is rarer medium, and the refractive index of the glass is mu2, which is the denser medium. This ray after refraction appear to come from a point O dash, and the refracted ray strikes on the another interface which having the radius curvature r2 and deviates away from the normal and meets at the principal axis at a point I, and this is the final image of the object O. Suppose distance of the object from the first surface is u, and distance of the O dash from the first surface is v1, and distance of the image from the second surface is v. Considering the lens is the thin lens, so the point P1 and P2 may be treated as a coincided point. So distances are measured from the common point. Using the formula for the spherical surfaces which we have earlier derived, that is mu2 by v minus mu1 by u equal to mu2 minus mu1 by r. We use this formula for the interface 1, then we will get mu2 by distance of the O dash is v1 minus mu1 by u, it will be equal to mu2 minus mu1, and the radius of curvature of the first spherical surface is r1. This is the equation number 1. Similarly, for other surface we will write, now the refractive index is mu1 by, and the image distance from the spherical surface is v minus mu2 by v1. Now the O dash act as the object for the interface 2, and it will be equal to mu1 minus mu2 by, and the radius of curvature of the second interface is r2. This is the equation number 2. So adding these two equations, we will have mu2 by v1 minus mu1 by u plus mu1 by v minus mu2 by v1, and it will be equal to mu2 minus mu1 by r1 and plus mu1 minus mu2 by r2. Here mu2 by v1 are common, so these will get cancelled because one is positive, one is negative, and the remaining is mu1 v minus mu1 u, that is equal to, and here we can take mu2 minus mu1 common, so remaining will be 1 by r1 minus 1 by r2. So on left hand side mu1 is common, so remaining is 1 by v minus 1 by u, that is equal to mu2 minus mu1 into 1 by r1 minus 1 by r2. Taking the mu1 on right hand side, we will have 1 by v minus 1 by u equal to mu2 minus mu1 by mu1 into 1 by r1 minus 1 by r2. This can be written as 1 by v minus 1 by u, that is equal to mu2 by mu1 minus 1 into 1 by r1 minus 1 by r2. So finally it is 1 by v minus 1 by u equal to mu2 by mu1 is the refractive index of the media 2 with respect to 1, so we can write it is mu21 or 1 mu2. Therefore mu21 minus 1 by r1 minus 1 by r2. This is the equation number 3. Now suppose u is infinity, that means object O is at infinity, so the image formed by the lens will be at the focus, so v will be equal to f. This implies that 1 by f minus 1 by infinity equal to mu 2 minus 1 into 1 by r1 minus 1 by r2. And this 1 by infinity is 0. So finally we will have 1 by f is equal to mu 2 1 minus 1 1 by r1 minus 1 by r2. This formula we have to remember. This formula is called the lens maker's formula. Using equation 3 and 4, if we compare right hand side are equal, so left hand side should also equal. Therefore, we can write 1 by f equal to 1 by v minus 1 by u. This formula is called the lens formula. Similar formula for the mirrors was called mirror formula, which we have already discussed, and which was 1 by f equal to 1 by v plus 1 by u. These formulas are applicable when rays are paraxial, that is, they are closer to the principal axis. Second is lens is thin lens, and third is that medium on both sides of the lens are same. Power of a lens is defined as P equal to 1 by f, where f is the focal length of the lens in meter and P is the power of lens in per meter or diopter, symbolized by capital D. We know that focal length of a convex lens is positive. This implies that power of a convex lens will also positive. Similarly, focal length of a concave lens is negative. This implies that power of a concave lens will negative. Two lenses in contact, say one of the lens is the concave lens or also called the divergent lens, and another lens is convex lens or the convergent lens. They have common principal axis and an object is taken at the principal axis, it is O. A ray falls on the first of the lens, and because it is divergent, so it diverges the ray. And this divergent ray appear to come from the point O dash on the principal axis. This divergent ray falls on the convex lens, which is a convergent lens, and it converges the ray, and ray meets the principal axis at the point I. This I is the image of the object O. Because lenses are thin, so the distances can be measured from the same point, and the distance of the object from the point is say u, and the O dash has the distance v1, and the distance of the image from the combination lens is v. Using the lens formula, which is 1 by f equal to 1 by v minus 1 by u for the two lenses, and these lenses are having the focal length f1 and f2 respectively. So for first lens, which is a concave lens, 1 by f1 will be equal to 1 by, and the image is O dash for the concave lens, so it is 1 by v1 minus 1 by u. For second lens, we can write 1 by f2, that is equal to 1 by, and the distance of the image is v minus distance is of the object is O dash, so it is v1. Now we add equation 1 and 2, we get 1 by f1 plus 1 by f2, it will be equal to 1 by v1 minus 1 by u plus 1 by v minus 1 by v1. 1 by v1 get cancelled. This implies that 1 by f1 equal to 1 by f2 equal to 1 by v minus 1 by u. V and u are the distances of the object and images if we consider the combination of the lens as the single lens. Therefore, This 1 by V minus 1 by U can be considered as 1 by F, where F is the final focal length of the combination. This implies that 1 by F will be equal to 1 by F1 plus 1 by F2. And because power is the inverse of the focal length, this implies that net power of the combination will be equal to sum of the individual powers.